this video, we'll talk through the bonding and structure and elements topic from Unit 1 of Higher Chemistry. By the end of this video, you'll be able to state the 4 different categories that elements can be separated into, give examples of elements from each of the categories, describe properties associated with each category. By looking at the bonding in each of the different categories of elements, we can explain why they have such a vast range of melting points. A melting point is a measure of the energy required to break the bonds which hold the atoms or the molecules together. If we have high melting points, that indicates that there's strong bonds being broken when it's melted. If you look at the data booklet, which has the melting points and boiling points, they can be separated into 4 broad categories. The first one we'll look at is metallic elements, and metallic elements are the ones that I have put in blue here. So we've got lithium, beryllium, sodium, magnesium, potassium, calcium, and aluminium. The next category we can look at are covalent network molecules. Covalent molecular can be separated into 2 subcategories where we have our diatomic elements and we also have our larger molecules. So phosphorus and sulfur are the larger ones, and the diatomic elements, hydrogen, nitrogen, oxygen, fluorine, chlorine, that you should be familiar with from before in chemistry. And the last category are called monatomic elements, and these are ones which exist on their own. It's important to be aware of the difference between structure and bonding. When we talk about our bonding, we are talking about covalent, ionic, and metallic only. If we're talking about elements, we cannot have ionic bonding. So when we are working with elements, we're either going to have covalent or metallic bonding if there's bonding present. When it comes to the structure, we can have molecular, we can have network, we can have monatomic, and we can have a lattice. We'll look at the 4 categories just now, and we'll kind of look at which words we use for which category. Start off with metallic elements. They have got a lattice of positively charged metal ions surrounded by a sea of delocalized electrons. And then there's an attraction between the positives and negatives, and that's what's going to hold it together, and that's what has to be broken in order to melt these chemicals. Typically find them in group 1 and 2, and remember we're looking most of the time at the first 20 elements. Moving on to, I've made this a subcategory of the diatomic covalent molecular, and these are where each molecule of the element has 2 atoms held together. You should be able to name the diatomic elements. If you're not too sure, a couple ways of remembering it. One would be Hinfockelbra, which stands for hydrogen, iodine, nitrogen, fluorine, oxygen, chlorine, and bromine. You might be given a different way of remembering it, but just be aware that if you're asked about these chemicals, they are diatomic covalent molecular. When we look at some larger molecules, including phosphorus and sulfur, we have P4 and we have S8. And again, that could be something that's useful to remember. So they're larger than diatomic, and we have 4 and 8 respectively. We also have carbon in the form of fullerenes, and these are fairly large structures, but the key is they are discrete. They do not keep on going. So they have a set number of carbons within them, and you have a whole variety of them. Typically C60 and C70 you may be asked about. We then move on to our covalent network elements, which are carbon, silicon, and boron. And you have different forms of these networks. So in carbon, we can have diamond or graphite, which have different structures within them, which allows them to have different properties. And lastly would be monatomic, which are our noble gases. They're already stable. They don't have to join on to anything else, and they exist as just a single atom on their own, or monatomic is how we would say that. We'll now look at some questions that you could be asked. They could give you a description of a type of bonding and ask you to identify which element this belongs to. So we have a solid substance with a lattice of positively charged ions and delocalized outer electrons. And we've got our options here. We'll go through it step by step. The first thing, if we've got positive ions and delocalized electrons, that means we've got a metallic element. And then we can rule out phosphorus, which is non-metal. And if we remember that graphite is carbon, that's also a non-metal. That's also going to be covalent rather than metallic. In order to distinguish between sodium and mercury, we are focusing in on the fact that it's a solid. That's telling us it has comparatively high melting points and boiling points. We go to the data booklet and we see that sodium has a higher melting point and boiling point, therefore it'd be a solid at room temperature. They could give you a question where they ask you about a specific chemical and ask you to describe the bonding and structure found in that. So you'll get your various different options, which it could be. For fullerenes are carbon. Carbon is an element, which means we're not going to have an ionic lattice. Carbon is covalent, which allows us to rule out our metallic lattice. And fullerene are carbon molecules, which means that our correct answer is covalent molecular. Another question I could ask you in this case is looking for the chemical which does not contain covalent bonds. We have our different options of answers. We've got all elements in this question, and if it's not going to have covalent bonds, that means we're looking at either a metallic element or a monatomic element. When we look through what we've got hydrogen and nitrogen, which are diatomic molecules, which would have covalent bonds, and sulfur is another covalent molecular, slightly larger than the hydrogen and the nitrogen. So we have got our monatomic element, our group A noble gas. Helium is the correct answer for that one. This question wants to know which of these is going to be a discrete molecule. We've got a list of our chemicals. If we get ourselves into a situation where we can't quite remember which bonding is in the particular elements, if we look at the melting points of each of the chemicals, that can give us some assistance. When you go to the data booklet and you look up these chemicals, you'll see that boron, carbon, and silicon have similarly high melting points, and sulfur is a lot lower than them. That would suggest that A, B, and C all have a similar type of bonding and structure within them, and that allows us to get that sulfur is the correct answer, because in terms of melting points, it's a lot different from the other three. On to the next type of question. We've got a specific named elements, and we're asked to look at the bonding and the structure present in each of them. We'll start with the bonding first of all. Our options for bonding are going to be ionic, metallic, and covalent. Because we're talking about elements, that means that it's not going to be ionic. Lithium is towards the left-hand side of the periodic table. It is a metal, and therefore it have metallic bonding within it. We then look at boron. Boron is on the right-hand side of the periodic table. Boron is a covalent molecule. In terms of structure, our options are lattice, network, molecular, and monatomic. We don't have metals for boron and nitrogen, therefore it's not going to be lattice. We don't have noble gases, therefore it's not going to be monatomic. That leaves us with network and molecular. Again, looking at the melting points and boiling points, we can see that boron has a higher melting point and boiling point, therefore it's going to be our covalent network, and that leaves nitrogen as our covalent molecular element. Hopefully you're now more familiar with the four categories of elements in terms of bonding and structure, being able to give examples from each of the categories and also describing properties that are associated with each of them. Thank you for watching. Goodbye.